We're going to continue our discussion of optics with lenses. A couple of things. You make sure you look at the announcement I sent out about the test. This test has a free response question on it. It'll actually have 2 free response questions on it. And the way we're going to do those, we want to do ray tracing. We've been discussing ray tracing with the mirrors. We're going to do ray tracing with lenses today. There's not really a good way to just do a multiple choice question on ray tracing without just also doing some free response. We got to do some free response. And so the way we're going to do it is you have 2 ways to be able to answer those questions. You're going to be able to, one, you're going to be able to just print off the test form. I'll give it the day of the test. There'll be a PDF that you can just download and print off. And then when you're done with all the multiple choice questions, you can go to that paper, you can do your ray tracing, and then you can just take a picture and upload it. And so when you take your test, you need to have a way of uploading pictures to your test, okay? So whatever device you use, make sure you have some sort of way that you can maybe have on your phone, just email it to yourself and then pull the email up from Canvas. I don't use those tools that like basically you can't like leave the screen. You're totally able to leave your tab, and so you'll be able to like pull up a picture from email. That might be the easiest way to do it, but that requires a printer because you do need the exact shapes in order to be able to do the ray tracing well. The alternative method is that you could, if you're on a laptop and you have Paint, just like basic Microsoft Paint application, if you're on Windows, just search Paint in your computer and you'll have it. You can download the image, so there'll be images in each of the questions. You can just download them, save them, and open them in Paint, and then you can just draw lines. And it's actually pretty easy because it'll make it straightforward. You don't even need a ruler. Just draw lines that show you the ray tracing, and it'll give you the image, and then just draw another line for the image. And so in order to make that happen, because I know this is new, it's a bit different, next week I'll have a quiz up that's like a practice test. And so it'll have a picture of the ray tracing, and it'll also have some sort of document you can download. And so you can, whichever method you like better, you'll have a chance to practice it and practice uploading it to the test. And that way, when the test comes around, you already know how you're going to be able to, or how you need to answer the question, whatever way you have. And so just letting you know that now. Let's get ahead into the notes. Let me know if you have any questions about any of that. The notes are pretty simple today. We're going over lenses. We're just doing some ray tracing again. They follow similar rules as last time. We have 2 kinds of lenses. We have convex, concave, and they have similar names, and they follow the similar shapes. However, what they do is different, okay? So convex shapes lenses, they have the same shape where like it kind of bulges out of the middle, kind of like convex mirrors where, we're bulging out of the middle when the light rays were coming in this side of the mirror, while concave mirrors look like this. And that's what concave lenses are. They have the cavity inwards to them. The difference is that we remember that concave mirrors reflected and diverged our rays. All the rays went away from each other, while concave mirrors, these rays went towards a focal point. They converged at some points, which gave you your image, okay? And so we called these diverging mirrors, and then these were convergent mirrors. They're opposites here. Convex lenses are converging lenses, and concave lenses are diverging lenses. And you actually need to know those terms. You need to know the converging lenses and diverging lenses because often, including on the homework assignment, we will refer to them as converging lenses over convex lenses, and we will say diverging lenses more often than we say concave lenses. You need to know both terms. You need to know that these are interchangeable. Here's the rules. I'll let you write them down, read them a couple times, and just pause here while you write it down. Just know that this is telling us about our parallel rays, what happens when we have a parallel ray coming in. This is our center ray, and this is our focal ray. And on the next slide, I will discuss more exactly what these points are saying. So those points, 1, 2, and 3, we had a parallel ray, a center ray, and a focal ray. Whenever we do our ray tracing, we're going to start by drawing a parallel ray, starting at the top of our object, like we did the mirror, going towards the lens. and we're going parallel to the axis, just like we did with the mirrors. The difference here is that instead of reflecting back like a mirror does, we're passing through the lens. But just like the mirror, when we bounced back, we went to the focal point on a converging mirror. Now we're on a converging lens, we're going to go through the focal point on the other side. So you can see that this first line goes past through the lens, and then it passes through the focal point. And we just keep drawing it until we see that the rays converge somewhere. The center line is the same for both this and the other lens. We'll see here in a second. Center lines, when they go through the center of the lens, so you can see the center right here, it just passes straight through and just keeps going. And then the focal lens, or the focal ray, we have a ray that goes through the focal point on the left side of the lens before it passes through. And when it hits the lens, it's going to go parallel. And then you can see that they all intersect right here, and that gives us an image. And you can see this image, it's a little smaller than our original object, and it's inverted, which means we have a real image. Here is our diverging lens. This one's a little bit weirder. So if you follow those instructions, it says first make a parallel ray. So we'll do a parallel ray. And then when we hit the lens, we're going to diverge. So we're actually going to go the opposite direction. We're not going to go towards the focal point. We're going to go directly away from it. And so what we're going to do is we're going to align our ruler with the focal point on the left side. And this point right here. So you line the ruler with those 2 points, and then you extend the line directly away from the focal point on the left side. Okay. And then when we do our focal ray, so we're actually going to skip the center ray for a second. Our focal ray, we're going to aim towards the focal point on the other side. So we're going to aim here from this point. And so that's where we put the rulers here. Let me do a different color to emphasize this a little bit. I'll just actually follow the colors here. We're doing blue for that one, so let's do blue. You start here and finish here. Okay. And so we put our ruler in between those points, and we draw the ray along that line until we hit the lens, and then we stop, because once we hit the lens, the light bends, and we know focal rays end up going parallel, and so we draw a line parallel to the axis. And you might see that these 2 rays will never converge. They are diverging, so they will never touch. And so if we want to find the image, we need to extend the rays backwards. And so what we're going to do is we're going to draw the dashed line that goes backwards here. And you can see if we do the same thing for the red, we extend this line backwards for the red, we have an intersection here, and that's why we have that virtual image there. And lastly, you can see the center ray follows the exact same thing as last time. It goes through the center and it just passes through like normal. And it also hits that point where we get our virtual image. Upright, smaller, virtual image. So let's actually practice doing our own ray tracing. So if you want to print out this slide, I think I uploaded all the slides already. You can do that. Otherwise, in class, we're going through the homework already, the homework packet. On, I think, the second page at the top, we're doing case 3. Case 3. We're doing it where we have some sort of image in between 2F and F. Anyways, either way, you need some sort of way to have a clear version of this. So, because these measurements, 2F needs to be exactly double F. These need to be measured lengths. They need to be all exact whenever you actually do these. Okay. So how do we do the ray tracing here? Well, we're going to do 2 lines. We're going to do one line that, whoops. Sorry. I don't know what just happened there. All right, we're going to do 2 lines. So here's our image. We're going to do the parallel line. Or here, there's our object, I should say, not the image. There's the object. Parallel line. Parallel line goes to the middle, hits right here, and then parallel lines go through the focal point. And so we just draw that line from there through the focal point and extend it onwards. Then we draw the focal ray. The focal ray goes through the focal point on the left side when we talk about converging lenses. And then when it hits the lens there, we extend it parallel afterwards. And you can see we get an image over here. And our image is inverted. I want to say it's supposed to be, it's actually a little bigger, but it's hard to tell in this case, but I think it's supposed to be bigger. Obviously, it's a little imperfect. I think my green is bent a little upwards. I don't think it's perfectly parallel, unfortunately. And then we know it's a real image because these light rays are actually converging here, right? They're not the dashed lines, they're solid lines. And so we know it's a real, and we also know from last time that real images are always inverted, and inverted images are always real. And so since it's inverted, we know it's real. Let's do a concave mirror. You might notice I never did the center line. I forgot to mention. Like last time with the mirrors, I'm only going to require you to do 2 other rays. You don't have to do the center line. You need to do the parallel ray and the focal ray when you do your lens diagrams. But if you want to skip the center line, you can. If you want to add it in, it's pretty easy to do. You just go from the top through the center and extend that line. And nice, that was pretty good. I intersected it exactly. So here, similar idea. Let's do one behind 2F. We'll do 2 rays. Again, we'll start with the parallel ray. So we get halfway through the lens. And I think for this one, sorry, I forgot to mention, I think it's the next page over on your homework. Case 1 or 2, whichever one is the furthest one back. It actually doesn't matter. Concave are basically the exact same pattern no matter what. There's not much difference between where you place your arrow. So parallel ray, parallel until we get to halfway through the lens, and then we're gonna bend directly away from the focal point. So I'm gonna make it clear on here because you can't see my ruler. I'm aligning the ruler between those 2 points, this point and this point right there. And I'm lining the ruler like such, and then I'm extending the ray directly away from the focal point. But I'm also gonna dash the line backwards through the focal point. Like that. And then we can do the focal ray. Again, on this one, the focal ray was towards the focal point on the left side. On concave lenses, we're gonna aim at the focal point over here. We're gonna aim for the focal point on the other side of the lens. And so we aim, so we hit the lens, and then we know focal rays end up parallel afterwards. And so I'm gonna do my best to align this ruler parallel to the axis, although it's a little difficult to do. And then we'll extend it parallel to the right. And then we also need to dash it parallel to the left. And we get an intersection over on the left side, right there. And so that is where our image lies. And we see that as upright, we see that it is greatly reduced, and we see that it is virtual because these light rays don't actually intersect there. We're just extending the light rays backwards to see where the light rays look like they're coming from on the other side of the mirror. Okay. With that, we're gonna do the math. Turns out the same equations from last time are the exact same equation we're gonna be using this time. And so this equation and this equation are the exact same equations we're going to use for lenses. So the focal length of a lens is equal to the object distance plus the image distance, or 1 over all those, right? And then the magnification is equal to the image's height over the object's height. And it's also equal to the negative of the image's distance over the object's distance. Now, what these points are saying is they're just conventions. We have to agree on what we're calling positive and negative, right? Remember that in kinematics way early in the year, we established rules for what we're saying positive, negative. Up was positive, down was negative. But we could have just as well said down was positive and up was negative. And as long as we all agree on that, our math is fine. And we all get the same numbers. But we have to all agree. And so that's what these are. These are general conventions we use in physics as what we're calling positive and negatives. And so we're going to say that the image or the distance of the image is always positive if it is on the side opposite the object. So the object will always have a positive. DO is always positive. And we're saying that the image distance is positive if it's on the opposite side of the lens. If it's on the same side of the lens, then we get a negative number. And so we know real images are always on the opposite side of the lens, so we get a real image. And then our image distance is negative if it's on the same side, which we get a virtual image in that case. Okay. And then for our focal point, we're going to say it's positive for converging lenses and negative for diverging lenses. Again, just a convention. You could have very much as well just said the opposite. And as long as we hold that, then our math is okay. But in this case, we're saying positive for converging, negative for diverging. Okay, so let's do a practice problem. A 0.2 meter high light bulb is placed 0.8 meters in front of a convex lens with a focal length of 0.6. Where does the image appear? What is the height of the image? We can go ahead and write our knowns down. I see 0.2 high. So that means our object's height is 0.2. And it's placed 0.8 meters away, so that's our object's distance. In front of a convex lens. Remember, convex is the same thing as a converging lens, which means that focal length is positive. So this focal length of 0.6, we know that's a positive 0.6. And we want to know where does the image appear and how high is the image. Well, I know F and I know DO. That means I can find DI by doing this equation. It's equal to DO plus DI. So 1 over 0.6 is equal to 1 over 0.8 plus 1 over DI. I think we get 1.67 is equal to 1.25 plus 1 over DI. We're going to subtract the 1.25 to the left side, and I think we get 0.4167, something along those lines, assuming you're keeping all the decimals in your calculator at the right time. I always remind you, make sure you're keeping exact values in your calculator. Don't round your numbers in your calculator to the very end. If we want to flip both sides, we just do the reciprocal of both sides. So we're doing di is going to be the reciprocal of 4167, which I believe you should get 2.4. So this is equal to 2.4. Great. And then now we can use the other equation to find our height. We know hi ho is equal to negative di do. And so plug in our numbers. Our height, image height is equal to 0.2, and it's equal to, or divided by 0.2 is equal to negative 2.4, which we just found out, divided by 0.8. You can do cross multiplication here. If you do that, you need to attach that negative sign to one or the other. It doesn't actually matter which one. So I'm going to go ahead and attach it up top to the 2.4. But again, it doesn't really matter. You can put it to the 0.8. Either way, you would get negative 3 on the right side, so they're equivalent. But you can do your cross multiplication. I don't really teach that. But if you know how to do cross multiplication, you're more than welcome to do that. Otherwise, I'm just going to teach simplifying. So if we want to simplify this equation and do the algebra involved, just simplify the right side. Put in your calculator, negative 2.4 divided by 0.8 gives you negative 3. Easy enough to do. And then just multiply by 0.2 on both sides. Right now, what we're looking for is being divided by 0.2, so we'd multiply by 0.2 on both sides to finish out the problem. And you get negative 0.6 meters, and that is our final answer. Again, check out that test quiz sometime next week. If you're taking the test online, you need to be able to do that. And then next class, you will have the other gizmos. Like I said earlier, I had a huge packet of gizmos. I had 2 for that one day. They were very long, and so that's why I reduced the work. And so we'll do the other gizmos next class, so there will not be notes next class, and then we'll have the review, and then we'll have the test next week. For those, I assume some of you virtual students are taking your AP tests that week. If you happen to be taking an AP test on the day of my exam, just communicate with me. Say, hey, Mr. Wilson, I take an AP test that day. Is there any way I can take the test on a different day? And I'll say, yes, that's totally fine. Like, I don't necessarily think AP tests are more important than my tests, but they are definitely more immediate and they need your immediate attention. And I don't want you to be taking an AP test and then coming home and with a dead brain, you're trying to take a physics test. That's just, it's not good. It doesn't actually show you what you know. And so I'd rather you just wait a day. So just communicate with me, whatever issues you have for the test with AP testing next week. It's at a weird time in the year. I am totally flexible. So with that, have a good day.